Hello and welcome to this Python tutorial. 3 steps down, 1 more to go, and this one final step that we have to do is the full connection step, which basically consists of making a classic ANN composed of some fully connected layers. And so why do we need to finish by this? Well, that's because we managed to convert our input image into this one-dimensional vector that contains some informations of the spatial structure or of some pixel patterns in the image. And now what we have to do, of course, is to use this input vector as the input layer of a classic artificial neural network. Because a classic artificial neural network, as we saw it, can be a great classifier for nonlinear problems. And since image classifications is a nonlinear problem, well, it will make a perfect job here to classify the images and tell if each image is the image of a cat or of a dog. So right now, since we already have our input layer, the only thing that we have to do left is to create a hidden layer. That is what we call a fully connected layer. So we will do that exactly as we did it when we built our classic artificial neural network in the previous section. And then we will need to add the output layer, just composed of one node because this is a binary outcome, cat or dog. And same, we will do it exactly as we did it in the previous section. So let's do it. We are going to start by adding the hidden layer, that is our fully connected layer. And so again, we take our classifier, paste, and then dot, and then we use the add method, then parenthesis, and then remember what we have to do. We need to use the dense function. That is the function that we use to add a fully connected layer. So parenthesis again, and now remember what we need to start with. The first parameter that we need to input here is output underscore dim, then equals, and now remember this output dim parameter is the number of nodes in the hidden layer. So now there is this big question again, how many nodes do we need to input here? So remember in the previous section we saw that there was no rule of thumb to choose a number of nodes in the hidden layer, but we saw that a common practice that leads to good results most of the time is to choose a number of hidden nodes between the number of input nodes and the number of output nodes. So here we have tons of input nodes because, we built 32 feature maps and each feature map contains many cells. So even if then we apply max pooling to reduce the size of our feature maps and divide them by 2, well then when we proceed to flattening to put all the cells of the feature maps into this one single vector that is the input layer of our fully connected layer, well we end up with a lot of input nodes. So we are not going to count all of them right now. We just know that we shouldn't take a too small number, and therefore we are going to choose here 128. Remember, this choice of numbers results from experimentation, and we need to choose a number that is not too small to make the classifier a good model, and also not too big to not make it too highly compute intensive. And therefore we need to experiment, but by experimenting on this output dim parameter, we realize that a number around 100 is a good choice. We could have picked 100, but it is a common practice to pick a power of 2. So we will go with this 128 hidden nodes in the hidden layer. And so now let's move on to the second and last parameter that we need to input in this dense function to add this fully connected layer as the hidden layer. And this second parameter is the activation function, of course, because the nodes in this hidden layer that we're adding are like neurons that we need to activate according to how much they can pass on the signal, that is, according to how much it is relevant for them to pass on their contribution to the final vote of the predicted class. And as in the previous section, since this is the hidden layer, well, the activation function that we'll use is going to be the rectifier activation function that is called ReLU. And that's it. That adds the fully connected layer, that is the hidden layer, in our CNN. And then the last layer that we need to add now is the output layer. And to add this output layer efficiently, we need to take this line here, copy it, paste it below, and now we just need to change the value of output dim and the activation function. Because now we're not using the rectifier activation function to return the probabilities of each class. Now it's going to be the sigmoid function. Remember, this is the sigmoid function because we have a binary outcome, cat or dog, and if we had an outcome with more than 2 categories, well, we would need to use the softmax activation function. But here we have a binary outcome, so it's the sigmoid activation function. Perfect, all good for the activation function. And now, of course, we must not forget to change the output dim parameter, because of course we're not expecting 128 nodes in the output layer. We are just expecting one node that is going to be the predicted probability of one class. And this class can be the dog or the cat. So let's replace 128 by 1. Here we go. And now that's done. We are done with the full connection step, because this full connection step only consisted of adding the fully connected layer, that is the hidden layer, and then the output layer to get the final predictions. So we are ready. We can select these 2 lines here and execute. And now here we go. The full connection step is done. And now eventually all our layers were correctly added to our convolutional neural network. And so now let's have a quick look at what we created. Here it is. That's the beautiful convolutional neural network that we just built through these 4 steps. So congratulations! When we remember our first simple linear regression model that we built in part 2, we made quite some progress here. So now we just need to compile the whole model, and that's what we'll do in the next tutorial. Until then, enjoy machine learning!